So we have our next speaker, Morteza Mardani from Nvidia. Morteza works primarily on generative AI at Nvidia and has held positions at Stanford, Berkeley, and I think you currently hold a position at Stanford right now in the electrical engineering department. He got his PhD at Minnesota in 2015 and was awarded for his contributions to large-scale data science with the Young Author Best Paper Award in the IEEE Signal Processing Society in 2017.
Hi. Thank you for the introduction, and hello, everyone.
Can you speak to the mic?
Sure, of course. So it's a pleasure to be here today at actually UIUC to give a talk. And so as the title suggests, my talk is actually about sampling diffusion models. David and Abhinav gave actually very good motivations about application of generative learning and specifically diffusion models for understanding geometry in vision and also robotics. But actually, I'm going to talk about and focus more on low-level computer vision and solving inverse problems using diffusion models. And I'll actually get deeper into, some specifics of diffusion models. And hopefully that would be useful for our audience. So this is actually quite pertinent with the recent wave in generative AI, which is transforming industries. And, there's a well-said quote from our company CEO, Jensen Huang, which said that we are switching from content search and retrieval to content generation. That actually motivates the changing the atmosphere industry about generative AI. And I'm pretty sure everybody in the room is amazed by the power of large language models, and especially ChatGPT for language generation, and has seen the tremendous potentials of that in the future. But we would like to have similar thing actually for vision too. So vision is an important modality, and generative diffusion models in particular have been very promising. They are not yet there actually, but they have been shown a lot of promises, especially for text to image generations. We have seen, several foundation models. So for stable diffusion, DALL-E 2 actually now should be updated with DALL-E 3 that came out last week, a couple of weeks ago, and also 85, which actually came out of Nvidia a few months ago. So that's why I would like to focus on diffusion models, which have been very promising actually for vision. So diffusion models are a class of deep generative models. And the problem of actually deep generative learning in general, it deals with learning distribution of data from finite number of samples. And it's in principle actually a density estimation problem. But of course, we don't necessarily need the density characterization. And what we would need at the end of the day is just a simple way to sample from it. For example, through neural networks. And that's what we do actually with diffusion models. And the landscape of deep generative learning has changed a lot actually over the years, from Bayesian neural networks and RBMs in 90s to actually more recent variational autoencoders, normalizing flows, and energy-based models, and most recently actually generative adversarial networks. But now there is a new big bang in generative learning actually by diffusion models. And I say this based on kind of observation from the CVPR actually submissions over the years. If we actually count the number of papers with the GAN or diffusion in the title, you could see that there was a peak at 2018 for GANs, but now diffusions are actually picking up. So then with this actually motivation, I'd like to give you the roadmap for the rest of the talk. I like to give you, because I'm coming from the industry side, I like to give you an overview of actually what's the NVIDIA's role actually in this area. And then after that, I'm going to give some introductions or, about diffusion models, in general, denoising diffusion models. And at the end, I would like to talk about actually a recent research work I was on sampling diffusion models where there are constraints, where we have observations or constraints actually on the downstream. And we would like to sample efficiently from diffusion models. So a lot of you actually may think like NVIDIA focuses a lot on the hardware and it's a hardware company, but actually NVIDIA has a lot of focus on software too. And in the case of generative AI, it's actually very challenging for software makers in general to add generative AI to their applications because generative AI models are not very easy to develop and deploy. So, and that's challenging because you can imagine that they would require tons of data. Just imagine ChatGPT-4 or Stable Diffusion, they would require internet scale data for training, and that would require actually cleaning and tagging the data for training. So the inference cost is also a bottleneck. You know, they would require, the inference is compute intensive for, you know, like for LLMs and even diffusion models even more. And it's complex to set up and scale. So another thing is that, you know, like customers want their, you know, diffusion models, for example, to be customized to their own data because of, you know, like the sensitivities and of in sharing data and privacy. So in order to, you know, doing all these three things, you know, like one needs AI expertise and also large amount of compute. So that's actually where NVIDIA is actually contributing to generative AI in general. So, and specifically on customizing models, NVIDIA has a focus on building customized, actually foundational models that convert or generate different modalities from text, image, speech, structural data, and even 3D signals. And in the last conference, in the last GTC conference, which is an NVIDIA actually company conference, is in March last year, NVIDIA announced AI Foundations, which is a foundry for, you know, like building generative models. And it's a cloud service essentially that helps with building custom AI models. And it helps actually the users to build, refine, and operate generative AI models on there. And it has different applications. It's actually NeMo, which focuses on language generation. It's an LLM. And there is a like biology version of NeMo. It's called actually BioNeMo. And there is Picasso actually for text-to-image generation, for visual art design, for vision. And all of this actually would run on a NVIDIA DGX cloud. And NVIDIA is actually partnering. It has some partnership and collaborations with Microsoft Azure, Google Cloud, and Oracle to host actually this their DGX cloud so that customers could run their generative AI models for training and inference there. So more specifically, actually, if you focus on Picasso, which is related to diffusion models and vision, so it's a foundry for custom generative AI models for visual design, and it could do text-to-image generation, text-to-video generation, and it could also do text-to-3D generation, all on the NVIDIA DGX cloud. So now, actually, let me talk about diffusion models. I would like to give you an introduction of the, you know, like the denoising diffusion models. And then after that, I'll talk about like how to sample from them for different downstream tasks when we have constraints. So diffusion models actually learn to generate using the principle of denoising. They consist of two processes. There is a forward noising process that gradually adds noise, and then there is which is the easy part of the process, and there is a reverse denoising process actually that tries to generate data from noise. So more precisely, so if you start in the training phase with the ground truth data, then we can gradually add noise, Gaussian noise. So, and then so that eventually the image or signal gets lost in noise. This is the forward diffusion process. It's a Markov process, and it has a very actually simple characterization. Essentially, given the previous time xt minus 1, the probability of xt is a normal distribution. So as a result, we could easily write the joint distribution given the, the ground truth data, which has a simple characterization. So if we actually think of the diffusion kernel, if you use a diffusion kernel, we can even do multi-step, characterization of that, because it's a Markov process. We can easily, write it as another Gaussian process, and then through the diffusion kernel, and then eventually we will end up with a, like a linear model, linear observation model. That's what be a way actually to think about it. That at each time t, at time step t of the diffusion model, so we would have a linear combination of the training data, which is the ground truth data, and noise by certain weighting, and we choose the weighting based on this beta, so that eventually, the signal gets lost, and then alpha bar is 0, and then we will end up with pure noise. So this is actually the forward process, the easy part. I just want you to remember this equation in the green box for the rest of the talk. This simple linear characterization. So it's interesting to know what happens to the distribution of the data in the forward process. In part because q of xt given x0, the conditional distribution is easy. But q of xt in general, it has a complicated distribution. Actually, it has a multimodal distribution in general. That's the diffuse data distribution that starts from the data distribution, and then at each time you can think of actually that it convolves the distribution with a Gaussian distribution, so that eventually it becomes a Gaussian distribution. So sampling from this distribution is easy, again, because we can sample from the training data, x0 first, and then sample from the Gaussian distribution of the diffuse distribution q of xt given x0. So this part is easy. But if we look at the backward process where we want to generate the data, so this becomes challenging. Going from the Gaussian to the original multimodal distribution, it's challenging, and that would require knowing the denoising distribution q of xt minus 1 given xt. So this distribution is complicated. Of course, if you look at the Bayes rule, we can see that it depends on the q of xt minus 1, which was the multimodal distribution that I explained in the previous slide. And this is very challenging, but what denoising diffusion models do, their main idea behind those is that they assume that this distribution of q of xt minus 1 given xt has a normal distribution, under the assumption that when we actually move in the forward process, the noise that we add at each time step is very small. So we add a very small amount of noise each time, and then we want to invert it. Then the assumption is that the denoising distribution also has a Gaussian distribution. So yeah, so then if the backward distribution is p of xt minus 1 given xt is a Gaussian distribution. That the variance we know is the sigma t, is the variance that we added in the forward process, but the mean is assumed to be represented or parameterized by a neural network. So the goal is to learn actually the mean of the distribution for the denoising distribution for the backward process, and which is parameterized by a neural network, which could be like a unit or a denoising autoencoder. In general, it's a autoencoder. It's a trainable network. So if we have this, characterization, then again, we can easily write a joint distribution based on this assumption. So which starts from noise, and then we have this actually backward distributions. And if we have this joint distribution, then, the classical way is to use maximum likelihood estimation for training. And then, but because the maximum likelihood is intractable, then people use the variational upper bound in general, which is a common practice. And also, if we reparameterize the mean of the Gaussian distribution using a residual just for convenience here, which is again another neural network, then we will end up with a very simple actually characterization for the training object, which is simply just the denoising. So what it does here is that this is just like the mean square error, training. So epsilon is the noise, IID noise that we know, we are aware of, and we sample it. And epsilon theta is the prediction for the noise. And then the input for the epsilon theta, which is a neural network, is the training objective, augmented with different levels of noise. And this is averaged out over all noise realization, all time steps, and all the, the distribution of the training data. So then if we, there is also, I just would like to mention that, what I talked about is about a discretized diffusion process, but it could be also extended to the, the continuous domain if you assume the time steps are very small. And interestingly, there is a stochastic differential equation characterization of that, which in the forward process, it simply actually adds a Brownian motion through the Wiener process to the signal at each time. So, and interestingly, the reverse process for the reverse process of this actually forward process SDE also exists, and it's kind of similar to the forward process, but there is an additional drift function added there, where the drift function here actually includes a score function, where the score function is the gradient of the log probability at each time. And actually, this is what we would work a lot actually for the rest of the talk. So yeah, overall, if you look at a training algorithm, the training actually looks very simple. We sample from the training data, and then we sample also just a uniform time step, and we sample noise, and then we take the gradient descent step based on stochastic optimization over the denoising objective at each time. So the training is very simple. So it just trains the score function here with different levels of noise. So, but once we have this train epsilon theta, train score function, then sampling is actually also easy. So we can just use off-the-shelf sampling algorithms. This is actually DDPM, suppose, but we could also use Langevin dynamics or MCMC type methods to do sampling based on the score function, using like ancestral sampling from capital T to a small t in the reverse process. But there are scenarios actually in practice that we have also some constraints, let's say in inverse problems, for example. And then these MCMC-based methods or Langevin dynamics actually based samplings are not working very well. So, and that's actually what I want to focus on the third part. And so for the sampling, actually, we have many downstream tasks, and we want to use only a single foundation models, for example, a stable diffusion, which is a rich prior, to solve different downstream tasks. So ideally, we don't want to retrain or fine-tune for each downstream tasks. So we want a kind of a sampler which is task agnostic, and also it's controllable. So we can control it, we can tune it. So it should be flexible actually for each specific task. So like it's in this case, one example is inverse problems, where they appear in different applications, for example, in image restoration or 3D rendering. And then we assume that we have some constraints already for sampling in terms of observations in image restoration, or we have some parametric model, like the rendering model, as in the 3D actually generation using NERF. And we want to impose actually this prior or this actually likelihood function in the sampling phase. So formally, the problem is an inverse problem that we have the observation y, which is related to the unknown x through this model f. The function f is actually a function that we know it. It's a forward model, and it could be linear or nonlinear. And we assume that the nu is is a Gaussian noise, for example. So as I said, if you want to use Langevin dynamics or MCMC-based methods, when we have this, observation model, the posterior for the score function posterior. The posterior score function becomes actually quite intractable because it's quite time dependent. And, like it, especially at the very first iterations of the reverse process where the noise level is pretty high. So there is no, good, approximation for that. So that's why if we actually be a little bit more specific about that, this is the score function that we would need. So we need the gradient of log of p of xt given y for sampling where y is the observation. So we can simply write it as a prior, which is given, let's say, by stable diffusion. The second part is easy, but the tricky part is actually the first part, which is the likelihood term. And the likelihood term, if xt is x0, this is Gaussian, this is easy. But when xt is, the different steps of the diffusion process, so this becomes quite complicated because it's related to x0 through this actually integration. So there is no actually simple way to get around it. So that's why we propose to use variational inference, variational approximation here, that we try to approximate the multimodal posterior distribution here using a simple Gaussian distribution and sample from it. And then the very first actually simple observations that we have at the beginning is that it's easy to show that this boils down to the KL optimization boils down to a score matching regularization. The first term is just the reconstruction term, but the second term is a regularization over the continuous diffusion trajectory. So where the first score function is the Gaussian score function, and the second one is the data score function. We want to match that with to the score function of a Gaussian distribution. So if we do actually some proper reweighting, like changing W tilde, then because in this form, it's a little bit complicated to optimize or even take gradient with respect to. So if we do have some proper reweighting for the W tilde, then actually we can recast it as a Fisher divergence. And then when it casts to a Fisher divergence, then taking gradient with respect to that actually becomes easy. So we still, if we assume that there is no dispersion, just for simplicity, in the variational inference actually here, and if you just use the Dirac assumption for the distribution, then under mild condition, actually, we can show that the gradient of the score matching regularization is simply just the difference between the score function and noise. So, of course, it's averaged out over, noise realization and time. But this has a very simple characterization, actually. So there is no, the first thing is to observe is that there is no Jacobian or backpropagation through the score function. It's just the forward evaluation of the score function, which actually give us the guidance term here. And also, the interesting thing is that this kind of resembles the regularization by denoising framework that actually we know in the context of denoising and solving inverse problems. Of course, that's for the deterministic scenario, where we don't have any generative prior, and we have just a single denoiser, and we want to, find a fixed point of the denoiser. So another interesting connection is that this is actually the special case of this formulation, and actually this framework is Diffusion, that I'm sure a lot of you in the room are familiar with. Which is just trying to do 2D, 2-3D generation using the score distillation loss, which ends up actually with exactly similar gradient. So we call this algorithm actually RedDiff, and red comes from regularization by denoising again. And if I actually summarize it here in this table, it looks very simple. So it looks like, if we use stochastic optimization, we can solve it now because we have an optimization formulation for that. So we just start with some initialization, and then we run different multiple actually gradient steps of the loss function now, or because we have also the gradient of the loss function available with any optimizer. So for example, we can use Adam optimizer. Of course, before that, we need to form actually the forward process, which is this actually line based on realization of time and noise at each time step. So the nice thing is that it actually kind of formulates sampling as a stochastic optimization, and then we can use a lot of off-the-shelf optimization algorithms which are available, even for accelerated sampling. So let me actually show you some results of this applied to different image restoration tasks. So image in painting is like it's a challenging image restoration task that we want to fill out the gaps here. And then this is actually the result of our algorithm that is using regularization by denoising, and then compare with other state-of-the-art methods like PyGDM or diffusion posterior sampling. We can see actually that it has better fidelity, that we could also observe it through the higher PSNR and other perceptual metrics too. So another interesting feature is that it actually becomes more efficient because it doesn't need any Jacobian or any backpropagation through the score function. It's just forward evaluation, as opposed to the previous work. So we have also tested that actually with image super resolution, and we could see that in terms of PSNR and like reconstruction actually does better. In terms of perceptual quality, actually it loses some performance, but in terms of like fidelity and reconstruction quality, actually it outperforms other methods. So we have actually applied it to other tasks in medical imaging. For example, the MRI reconstruction, where the task is to reconstruct. It's still a linear task actually, where the task is to reconstruct like a ground truth image from Fourier observation, partially observed Fourier observations. And if you just do like partial Fourier inversion, we end up with this zero field image, which has a lot of aliasing artifacts. And then so our method actually could also solve that problem and compare with Langevin dynamics, actually based samplers that I mentioned at the beginning of my talk. It has much better fidelity and robustness. You could see actually that the Langevin dynamics based sampler here in this context that would introduce some hallucinations. So we could see also the performance in terms of the quantitative metrics. And then we also applied it actually for nonlinear tasks. It's more interesting for nonlinear tasks because, like the previous work which can handle nonlinear tasks is this diffusion posterior sampling. And that is actually very sensitive to, like optimization, to tuning and learning rate adjustment. But we could actually get much better performance compared with that for the different nonlinear tasks as well. So another application of that actually was for text to 3D generation, where we compared the performance of that with Diffusion. Of course, with the intuitions that we got with the connection with Diffusion, we could, improve the tuning and also the sampling of the Diffusion, so that for text to 3D generation, actually, we could get better quality than Diffusion as well. So, yeah, so I think this is actually the conclusions. And the punchline is that generative AI is actually rapidly changing how we work with data and applications. Nvidia is actually trying to help with the full stack from software to the hardware to compute. And also diffusion models in particular, which are inspired by stochastic differential equations, are very powerful for text to image and 3D generations in this context. And so what I wanted to, give an algorithm and details about in this talk was how we can sample from foundation models without fine-tuning or retraining them in a task agnostic fashion, essentially in a plug and play manner. So, and then, with the framework of regularization by denoising, we could cast sampling as an optimization, which actually gives us interpretability, and it also gives us the controllability. So, and this actually was an interesting connection, makes an interesting connection with generation, with regularization by denoising, which actually leverages the implicit prior of the denoising for sampling. So yeah, that's it actually for the talk. And then the materials you could actually find online. The code base is also available online. And I also want to, acknowledge and thank my collaborators who helped a lot actually with this project. And at the end, I want to take the opportunity to, encourage students and postdocs, to apply for openings that we have at NVIDIA, both full-time and, intern positions. So you could actually reach out to me and email me your CVs, and if you are interested, and then I can give you actually more advice what to do next. So, and yeah, that's it. So if there are any questions, I would be happy to address.
Thank you. Thank you for your great talk. So I have a small question. So can the variational inference method apply to other types of generative models? So for example, latent diffusion models?
Well,
in dealing in addressing the inverse problems.
Right, it's a good question actually. It could be applied in the same way to latent diffusion models. But in the case of a stable diffusion, it actually becomes more tricky. We worked on that. And in the case of a stable diffusion, because it requires a decoder inversion, because the optimization variable or optimization is going on in the latent space, then you need to do back and forth between the, the RGB space and also the latent space. In the case of a stable diffusion, it's a little bit more tricky because the inversion is harder. But in principle, yes, it could be applied as long as we have a good inversion algorithm from output of the decoder to the latent space.
Okay, thank you. And another small question. So, so in the forwarder, in the observation model, you assume that the noise is ideal Gaussian noise. So, and do you assume that the noise variance is known?
Noise variance is known, right?
So how about what if the noise variance is unknown?
Well, that becomes more of a blind problem. So it actually becomes a different problem, completely different problem, I would say. And we could probably use, noise estimation problems, noise estimation algorithms, noise variance prediction algorithms, actually at each step, probably in a blind fashion.
Yeah, thank you. Thank you.
Sure.
I have a broader question. Earlier at the very beginning of the talk, you said there was two big bangs. One was GANs and then now diffusion models. So is there a fundamental reason as to why diffusion models work better, or is it something still we don't know? It's just simply empirical?
Well, empirically, it's actually maybe more empirical. So we have enough empirical observation that, for example, GANs have mode collapse. So, but the diffusions actually are much better in covering the modes. So that's one thing. Another thing actually that I wanted to point out, it's deployment of diffusion models. Also, I found it's easier, especially for inverse problems, because you have just the simplest score function, which is the gradient of log probabilities, and you can easily plug it into samplers for downstream sampling. Right. And of course, we know that the optimization of GANs is much harder, but diffusion's optimization is just the denoising. It's actually more time consuming in general, because you need to, because it's an expectation over 3 variables. For stochastic optimization would require actually a lot of iterations, but the training is stable. It's just because it's just a denoising.
So is that also the reason why there is less mode collapse? And
that could be a reason, yeah, because it's not a game between 2 non-convex objectives. So it's just a simple objective.
Thanks.
So I have a question. So I guess since you can do this smarter sampling, can you somehow sample around the fact that we're seeing these weird artifacts when we do like traditional random sampling? So like the stuff that Abhinav and David showed, where we see like multiple fingers or something, can we somehow avoid these effects?
Yeah, actually, it's a very good point. If we have, like there are some efforts going on. There are actually some works out on compositional generation. For example, layout GPT. That if you have layout information that, for example, you get from language models, which give you the local correlations of the objects, let's say around bounding boxes around the objects, and then you could just use them in a sampling phase. That they would appear as some sort of covariance matrices, actually, that you can actually integrate them with the sampling and then just modify the sampling.
One of the things I thought was interesting, I don't know if this picture is generated or not. Is it?
It's generated. Yeah.
Okay.
Stable diffusion.
Okay, good. But that could be a natural picture. I could sit there and take the picture, and I would then be able to have natural scene statistics that would, be very similar. But what I think is interesting that these models also can generate things that don't have these type of statistics, like you saw some MRI imagery.
Right, right.
Can you say more about that? Why you think that is true? It's very good at generating what I would call natural scenes, and we've certainly done this with also MRI, and I'll talk a little bit about that this afternoon, but why do you think it's so that it can also generate these sort of non-natural scenes? That's not a natural scene.
Yeah, exactly. But let me actually clarify here that we use a pre-trained MRI model here. We are not using a pre-trained stable diffusion here for MRI sampling. So it's been trained on the distribution of like MRI data based on there is a big data set. It's called fast MRI data set that I'm sure you know. So
of course, but the model still works on these unnatural scenes.
Right.
Yeah.
So it seems that they work actually and the neural net. That's the nature of the denoising unit actually was originally introduced for medical image segmentation. So it's very good actually at representing medical images.
For the MRI reconstruction, does it tend to reconstruct an image of like the normal brain or organ, or can it pick up on smaller details that might give an imperfection as well, or an abnormality?
So if I understand your question, so you're saying that if it can pick up abnormalities, smaller abnormalities?
Yes.
So, well, that's more of a fundamental task. If we have enough if we don't have enough observations, enough Fourier samples, there is no way to get those. Even if you have a very strong prior, even if you have like a stable diffusion of MRI. So, but definitely having a good prior would help. So I would say it's a combination of two things: both having sufficient observations about the pathology. About the tumor, for example, the image, and also having a rich prior. Yeah.
Thank you.
Sure.
Oh, thank you for the talk. It was quite interesting. So in like slide, I think 34, you have like samples of imaging painting, and some of the samples have like blurred backgrounds, right? The earlier methods, but like your method was able to reconstruct it quite sharply. And do you have like guesses why it was happening in previous models, why the background was blurred? I'm just wondering.
Right. So I think it's this score function that actually guiding the sampling, and it may end up somehow in a part of the manifold, which apparently this has the largest likelihood. So the guidance might be off. Yeah, but it's hard to tell in general what is specifically going wrong there.
So essentially your method helped to do better sampling, so it would be like sharper generation, right? Like
Right. So that's the point. Because these are under sampled problems, so there is a lot of uncertainty here, and some models tend to average out more uncertainty rather than actually going and picking up the point. So the point is, because like our algorithm is a map estimator, so map estimator goes and picks the highest probability, which is the sharpest image. But other methods are not actually map estimators, so they could average out over the uncertainty.